Every major tech company is racing to build a quantum computer, but one of them tried something so radical, so unproven, that most physicists thought it would never work. And when it first seemed to work, it turned out to be a mistake so public it made international headlines. This is the inside story of Microsoft's Majorana gamble. And it is stranger, slower, and more human than any clickbait headline could capture. To understand why this story matters, you have to understand what Microsoft was actually chasing. Every computer you have ever used, from the phone in your pocket to the servers running the internet, works with bits. A bit is either a 0 or a 1. It is simple, it is reliable, and it has powered 70 years of digital progress. Quantum computers throw that simplicity away. Instead of bits, they use qubits, and a qubit can exist in a strange in-between state, part 0 and part 1 at the same time, until the moment you measure it. That property, called superposition, along with another strange behavior called entanglement, is what gives quantum computers their theoretical power. For certain kinds of problems, from simulating molecules to breaking encryption, a working quantum computer could outperform every classical computer on Earth combined. But there is a catch, and it is a brutal one. Qubits are almost unbelievably fragile. The tiniest vibration, the faintest stray electromagnetic field, even a small shift in temperature can cause a qubit to lose its quantum state. Scientists call this decoherence, and it is the single biggest obstacle standing between quantum computing as a laboratory curiosity and quantum computing as a real, useful technology. Companies like Google and IBM have tackled this problem by building qubits out of superconducting circuits, and then wrapping those qubits in layers and layers of error correction, using extra qubits just to catch and fix the mistakes made by other qubits. It works, but it is expensive and it requires enormous overhead. To build a genuinely useful quantum computer this way, you might need thousands of physical qubits just to create a single reliable logical qubit. To put that overhead problem in perspective, some estimates suggest that building a single stable, logical qubit out of today's leading superconducting hardware could require on the order of 1,000 or more noisy physical qubits working together, just to catch and correct the errors that inevitably creep in. Multiply that by the number of logical qubits you would need to run a genuinely useful algorithm, and the scale of the engineering challenge becomes staggering. It is a bit like trying to write a perfect, error-free letter by hand, except you need 1,000 people proofreading every single word you write in real time, just to make sure nothing gets garbled along the way. It can work, and companies have shown real progress doing it, but it is expensive, it is slow to scale, and it demands enormous physical infrastructure just to keep errors under control. Nearly 2 decades ago, Microsoft decided to bet on a completely different approach. Instead of building fragile qubits and then correcting their errors after the fact, what if you could build a qubit that resisted errors by its very nature? What if the protection was baked into the physics itself, rather than bolted on afterward through software and redundancy? That idea is called topological quantum computing, and it is built around one of the strangest, most elusive objects in modern physics, the Majorana particle. The story of that particle actually begins almost 90 years ago, in 1937, when an Italian physicist named Ettore Majorana proposed something unusual. Most particles in the universe have a distinct antiparticle, a kind of mirror image twin with opposite charge. An electron has a positron. A proton has an antiproton. But Majorana theorized that certain particles could be their own antiparticle, a mathematical oddity that fascinated physicists for decades but remained purely theoretical. Majorana himself vanished mysteriously in 1938 while traveling by ship, and his fate has never been fully explained, which only adds to the mythology around the particle that bears his name. Historians and physicists have spent decades speculating about what happened to him, from a possible suicide to a deliberate disappearance into a monastery or quiet new life abroad, and no definitive answer has ever surfaced. It is an unusually mysterious footnote for a scientist whose name would go on to anchor one of the most ambitious corporate research programs in modern technology, nearly a century after he vanished without a trace. That strange origin story is part of why the Majorana particle has always carried a certain mystique within physics, well before any company got involved. It sat for decades as an elegant mathematical possibility with no confirmed home in nature, discussed in graduate seminars and theoretical papers, but never actually observed in a laboratory in its purest fundamental form. Some physicists spent entire careers searching for signs of it in exotic settings, from neutrino physics to the interiors of specially engineered materials, without ever reaching a fully settled conclusion. That long, patient, occasionally frustrating hunt is the scientific inheritance that Microsoft's engineers stepped into when they decided to chase an engineered version of the same phenomenon inside a chip. For most of the 20th century, the Majorana fermions stayed a footnote in textbooks, a strange solution to an equation with no confirmed physical example. Then, in the early 2000s, physicists realized something exciting. You did not need to find a fundamental Majorana particle floating around in space. You might be able to engineer something that behaved like one, inside a carefully constructed material at incredibly low temperatures. These engineered stand-ins are called Majorana zero modes, and they appear, in theory, at the ends of specially designed nanowires made from a semiconductor and a superconductor layered together when the whole system is cooled to near absolute zero and placed in a precise magnetic field. Here is why physicists got so excited about this idea. If you can create and control Majorana zero modes, you can, in theory, use pairs of them to store quantum information in a way that is naturally protected from small disturbances. The information is not sitting in one fragile spot, vulnerable to any nearby vibration. Instead, it is stored non-locally, spread across the underlying topology of the system in a way that is much harder to accidentally disturb. Physicists sometimes describe this using the idea of braiding, where moving these particle-like zero modes around each other in a specific pattern performs quantum operations, encoded not in a fragile physical location, but in the shape of the path itself. If it worked the way theory predicted, this approach could need dramatically fewer physical qubits to create a stable, reliable logical qubit compared to the brute force error correction used by competitors. It was an elegant idea. It was also, for a very long time, entirely unproven, and Microsoft chose to build an entire division of its quantum computing strategy around finding it. This was, by any reasonable business standard, an unusual gamble. Most corporate research divisions want a fairly clear line of sight to a working product within a handful of years, especially when the sums of money involved reach into the hundreds of millions of dollars. Microsoft's leadership instead greenlit a program that was explicitly built around chasing a piece of unproven fundamental physics, one that might, after years of effort, simply turn out not to be achievable in a controllable, engineerable way at all. That is a very different kind of bet than incrementally improving an already working technology. And it says something about how highly the company's leadership valued the theoretical payoff if the approach ultimately succeeded. Beginning around 2006, Microsoft started pouring resources into this approach, eventually establishing a network of research stations under a program often referred to as Station Q, with a particularly important hub of experimental work based in Sydney, Australia, alongside theoretical and materials science teams spread across the Netherlands, Denmark, and the United States. This was not a quiet side project. It was a long-term, expensive commitment to a technology that had not yet been proven to exist in a usable form. Rival companies were racing ahead with superconducting qubits that already worked, even if imperfectly. Microsoft was betting on a particle that some physicists were not even convinced could be reliably created and detected at all. For years, progress moved in small, incremental steps, mostly invisible to the public. Then, in March of 2018, everything seemed to change. A team including a physicist named Leo Kouwenhoven, based at Delft University of Technology in the Netherlands, and also affiliated with Microsoft, published a paper in the prestigious journal Nature titled Quantized Majorana Conductance. The paper reported experimental evidence in the form of a specific electrical signature called a conductance plateau that appeared to confirm the existence of Majorana zero modes in a nanowire device. It was treated as a landmark result. Coverage spread through major outlets, and Microsoft's own director of quantum computing business development was quoted telling the BBC that a commercially relevant quantum computer solving real problems could arrive within 5 years. For a company that had staked its long-term quantum strategy on this exact physics, this looked like vindication. But within the research community, not everyone was convinced, and a small number of physicists began asking a very simple, very uncomfortable question. Could they see the raw data behind the plateau? Two researchers in particular, Sergei Frolov at the University of Pittsburgh and Vincent Murick, requested the underlying data from the 2018 experiment and began combing through it carefully. What they found was troubling. According to their analysis, certain data points that contradicted the paper's central claim appeared to have been excluded from the published figures. An axis scaling on some of the graphs appeared to have been adjusted in ways that made the evidence for a clean conductance plateau look stronger than the raw numbers actually supported. Frolov later told reporters that once you looked at the fuller dataset, the case for a genuine Majorana signal essentially disappeared. This is where the story stops sounding like a straightforward tech triumph and starts sounding like a case study in how science is supposed to police itself, sometimes slowly, sometimes painfully, but ultimately in public. The paper received a formal expression of concern from Nature in April of 2020, a kind of official flag telling readers that the reliability of the results was now in question. Delft University of Technology launched its own independent investigation through a scientific integrity committee. That committee ultimately agreed with the critics that the presentation of the data had been misleading, but importantly, it found no evidence that the errors had been intentional, describing the issue instead as a serious failure of rigor rather than deliberate fraud. In March of 2021, the authors formally retracted the paper. Their statement did not dodge the problem, They wrote that they had failed to convey the full picture of the measurements in the device to the appropriate standard of scientific rigor, an unusually direct admission for a retraction notice. It was, without exaggeration, one of the most closely watched retractions in recent physics history, precisely because so much commercial and scientific weight had been placed on the original result. For Microsoft, this was a real setback, and it played out in full public view, not behind closed doors in some hidden facility. Skeptics who had already doubted the topological approach felt vindicated. Some in the broader quantum computing field wondered whether the entire Majorana strategy was built on wishful thinking rather than solid physics. It would have been easy, at this point, for a company under shareholder pressure to quietly reallocate its resources toward the qubit technologies that were already demonstrably working, the superconducting circuits that Google and IBM were scaling up year after year with visible, incremental progress. There was also a wider ripple effect across the field that is easy to overlook. The 2018 retraction did not just embarrass one team at one company, it cast a shadow over an entire subfield of physics that had, for years, been racing to find and characterize Majorana zero modes in various experimental setups. Just months after the Nature retraction, a separate paper published in the journal Science describing a related approach to creating Majorana zero modes, and also involving researchers affiliated with Microsoft, received its own formal expression of concern after outside scientists raised similar questions about how the data had been presented. Taken together, these episodes fueled a broader wave of skepticism across the research community about claims of Majorana detection in general, making it considerably harder for any team, Microsoft included, to convince peers that a new result was solid rather than another case of researchers seeing the signal they wanted to see in noisy, ambiguous data. Instead, Microsoft's quantum team did something less dramatic, but arguably more interesting. They went back to the lab. Following the retraction, the team, now working closely with independent experts and subjecting their methods to far more rigorous outside scrutiny, spent years rebuilding both their experimental techniques and their credibility. According to the company's later accounts, they took the criticism from the physics community directly, reanalyzed their data using more careful and more transparent methods, and published new work that invited independent examination rather than avoiding it. This period, roughly from 2021 through the following few years, was quiet by design. There were no dramatic press conferences. There was instead unglamorous, methodical laboratory work, refining materials, refining measurement techniques, and slowly trying to separate a genuine Majorana signal from look-alike phenomena that had fooled researchers before, such as so-called Andreev bound states, which can mimic some of the same electrical signatures without being the real thing at all. This distinction between a genuine Majorana zero mode and a convincing look-alike turned out to be one of the central technical battlegrounds of the entire saga. Andreev bound states can arise in similar nanowire devices under similar conditions, and under certain measurement setups, they can produce conductance signatures that look deceptively similar to what theory predicts for a true Majorana zero mode. Telling the two apart requires extremely careful, multi-pronged experimental evidence, not just a single clean-looking plateau on a single graph. Part of what made the 2018 paper so vulnerable to criticism was that it leaned heavily on one particular type of measurement. And critics argued that a more rigorous approach would have required corroborating evidence from multiple independent angles before publishing such a bold claim. That lesson clearly shaped how the team approached its work in the years that followed, pushing them toward more redundant, cross-checked measurement techniques designed specifically to rule out these kinds of imposter signals. Then, in February of 2025, Microsoft resurfaced with an announcement that once again made global headlines, though this time under very different circumstances than the 2018 episode. The company unveiled what it called Majorana 1, described as the world's first quantum processing unit powered by what Microsoft named a topological core. Alongside the announcement, the team published a new peer-reviewed paper in Nature and shared additional data at a Station Q gathering with the broader research community. According to Microsoft, the chip demonstrated a hardware platform built from a newly engineered material combination, indium arsenide acting as a semiconductor layered with aluminum acting as a superconductor, cooled to temperatures near absolute zero and shaped into nanowires capable of hosting Majorana zero modes at their ends. Microsoft described this new state of engineered matter as a topoconductor and said the resulting chip contained 8 topological qubits, with a long-term design roadmap aimed at scaling toward as many as 1 million qubits on a single chip. This time, the company was noticeably more careful in how it framed the claim, at least in its formal scientific publication, but the public-facing press release still went further than some scientists were comfortable with, describing the device as powered by a topological core and suggesting it could put quantum computers capable of solving meaningful problems within years rather than decades. Nature's own editorial team added a notable caveat alongside the paper, stating clearly that the published results did not, by themselves, represent definitive evidence for the presence of Majorana zero modes in the devices, but rather demonstrated a new platform and measurement approach that could support future experiments aimed at proving their existence. That distinction might sound like a technicality, but to physicists, it is everything, and it explains why the announcement landed with such a mixed reaction at one of the most important physics gatherings of the year. Weeks after the Nature publication, the American Physical Society held its Global Physics Summit in Anaheim, California, and Microsoft's quantum team leader, a physicist named Chetan Nayak, took the stage to present the evidence directly to thousands of his peers. According to those who tracked attendee activity at the 14,000-person conference, Microsoft and Nayak were the two most searched terms in the entire event program, a sign of just how much attention and how much residual skepticism still surrounded the company's claims after the 2018 episode. Nayak's presentation was intended to offer more direct evidence than the press release alone had provided. Reaction in the room, and in the broader research community afterward, was genuinely split. Some researchers saw meaningful, credible progress toward a real topological qubit platform. Others argued that what had been shown was still primarily a demonstration of a readout method, a way of measuring the state of a device rather than conclusive proof that the underlying Majorana physics was actually present and behaving as predicted. Independent technical analyses published in the months that followed dug even deeper into these distinctions. Some pointed out that the publicly available demonstrations showed a method for reading out information from the device, but did not yet demonstrate actual quantum processing operations being performed on the zero modes themselves, and did not test how long the two-level quantum system could maintain coherence, a critical benchmark that other qubit platforms, including the superconducting qubits used by competitors, routinely report as a matter of course. In other words, Microsoft had shown a promising new piece of hardware and a clever way to measure it, but had not yet shown the kind of full, unambiguous operational proof that would put the 2018 controversy fully to rest for every skeptic in the field. So where does that leave the story, and why does it matter beyond the walls of a physics conference? It matters because this is what real scientific progress actually looks like, and it rarely resembles the neat, dramatic arc of a thriller. There was no secret underground facility, there was no unexplained disappearance of staff, no sealed vault of forbidden findings, no government conspiracy silencing inconvenient results. What actually happened was public, documented, and in many ways more compelling than fiction, precisely because it was real. A company bet nearly 2 decades and untold hundreds of millions of dollars on a physics approach that most of the field considered a long shot. That bet blew up in the most public way imaginable, with a headline-grabbing result being formally retracted after independent scientists caught inconsistencies in the underlying data. Rather than walking away, the team returned to fundamentals, rebuilt their methods under far greater scrutiny, and came back years later with a new device and a new peer-reviewed paper, one that still faces real, substantive, ongoing skepticism from experts inside the very community whose approval Microsoft most needs. That tension is exactly where the story stands today. Microsoft has a working piece of novel hardware, genuinely new materials science, and a published pathway that some serious researchers find promising. It also has a research community that remembers 2018 very well, and that is, appropriately, demanding a much higher standard of proof before accepting extraordinary claims a second time. Microsoft executives themselves have been noticeably more measured about timelines and interviews since the 2025 announcement, with one company vice president telling reporters that the team wants to reach a few hundred qubits before anyone should be talking seriously about commercial reliability. That kind of caution stands in sharp contrast to the confident 5-year prediction made back in 2018, and it suggests a company and a team of scientists that learned something real from its very public stumble. There is also a broader competitive backdrop worth understanding. Microsoft is not alone in this race, and it is not necessarily even the front-runner by conventional measures. Google and IBM have continued to scale up their superconducting qubit systems, publishing steady incremental improvements in qubit counts and error rates that, while requiring heavy error correction overhead, are measurable and independently verifiable year over year. Smaller specialized companies, including IonQ, working with trapped ion qubits, and Rigetti Computing with its own superconducting approach, are pursuing yet other paths toward the same ultimate goal, each with its own trade-offs in speed, stability, and scalability. National research programs in China, the European Union, and elsewhere are pouring public funding into their own quantum efforts as well, treating the technology as a strategic priority on par with advanced semiconductors, which only adds another layer of competitive pressure on top of the already intense rivalry between private companies. Topological qubits, if they can ultimately be proven and scaled the way Microsoft hopes, could theoretically leapfrog these approaches by needing far less error correction overhead per useful logical qubit. But that theoretical advantage only matters if the underlying physics holds up to the same rigorous, independent, reproducible standard that any other extraordinary scientific claim must meet, especially one that has already failed that test once in a very public way. Why should anyone outside a physics laboratory care about any of this? Because the stakes attached to quantum computing are genuinely enormous, and not in a vague, hand-wavy sense. A sufficiently powerful, fault-tolerant quantum computer could, in theory, break many of the encryption systems that currently protect financial transactions, private communications, and government secrets around the world, which is exactly why governments and intelligence agencies are already investing heavily in what is called post-quantum cryptography, encryption designed to remain secure even against a future quantum computer. On the more optimistic side, the same technology could dramatically accelerate the simulation of complex molecules, potentially speeding up the discovery of new medicines and materials in ways that would be practically impossible for classical computers, no matter how powerful. It could also reshape fields like logistics and financial modeling, where certain kinds of optimization problems scale so poorly on classical hardware that even small improvements from a working quantum system could translate into massive real-world savings. These are not distant, abstract possibilities dreamed up for a press release. They are the concrete reasons why governments, universities, and competing tech giants have collectively poured tens of billions of dollars into this field over the past decade, even knowing that a fully fault-tolerant, large-scale quantum computer may still be years or even decades away. Whichever company or approach eventually crosses the finish line to a stable, scalable, genuinely fault-tolerant quantum computer will be sitting on one of the most consequential technologies of this century, which is exactly why Microsoft was willing to spend 20 years and endure one of the most publicly humbling retractions in modern physics, rather than quietly abandon a difficult idea. So, no, there was no secret lab that was mysteriously shut down overnight, and no hidden discovery too dangerous to reveal. The real story is something arguably more interesting. A 2-decade scientific gamble that very publicly failed once was rebuilt in full view of a skeptical scientific community, and has returned with a genuinely novel piece of hardware that is still, right now, in the middle of being tested, challenged, and scrutinized by the very people whose trust it needs to earn back. Whether Majorana 1 and its successors ultimately prove that topological qubits are the future of computing, or whether they become another chapter in a long, difficult, occasionally humbling scientific pursuit that has not yet reached its destination, will be decided the same way the previous. A more painful chapter was ultimately decided, not in secrecy, but in published papers, replicated experiments, and open, sometimes uncomfortable scientific debate. That process is still playing out today, in laboratories, in journals, and at physics conferences around the world, which means the real ending to this story has not been written yet, no matter how much any single press release might want you to believe otherwise. And unlike the version built for clicks and shock value, this one is verifiable, it is ongoing, and it is far from over.